Good evening. Welcome back to the module Communication Theory, Learning Outcome 3, Topic 10. In that topic, we are going to discuss thermal noise in RC network and what do you mean by bandpass noise. In previous session, we studied about the what do you mean by noise and what are the basic type of noises occurring in the communication systems. Okay, the noise is an unwanted waves which disturb the communication system and the signal processing of the communication systems. There are three basic type of noises available in a communication system, such as short noise, thermal noise, and white noise. Short noise is occurring due to the discrete nature of the current flow in any electronic devices. For example, diodes, transistor, or photodetector. The discrete nature of current flow happening due to that in the electron emission from the cathode terminal of the electronic devices, and it is modeled as a current pulse. So from this current pulse, we can find out what is the that average power of the short noise. Next, coming to the thermal noise, the thermal noise is occurring due to the random motion of the electron in an electronic conductor. Okay, for example, we can consider the thermal resistor. So in the thermal resistor, the thermal noise is occurring, and we can find out um, what is the noise power of the thermal noise by using Thevenin theorem and Norton theorem. We can draw the equivalent circuit for the thermal resistor using Thevenin theorem or Norton theorem, and then from that we can find out what is the mean square voltage or mean square current of the thermal resistor. Okay. Next, we studied about the white noise. So the noises in the communication system generally modeled as a white noise because the noise in the communication system has the properties, similar properties of the visible light spectrum, which means that in white noise, all the frequency components having that same power for the large frequency range. So that we are calling the noises in the communication system as a white noise. So with that continuation, today's session we are going to discuss about the thermal noise in RC network, and then what do you mean by bandpass noise? When how the bandpass noise is occurring in a communication receiver. So thermal noise. So this content actually prepared from the textbook Bruce Carlson. Even though in previous session we discussed the same the thermal noise, that book is we followed that Simon Hawking. This session we followed that Bruce Carlson. Okay, so the definition for the thermal noise. Thermal noise is the noise produced by the random motion of charged particle in conducting media. For example, thermal resistor, right? And as per kinetic theory, the average energy of any particle is the product of K and T, right? Here, where K is the Boltzmann constant and T is the absolute temperature, right? And okay, so then we can use the central limit theorem. By using central limit theorem, we can find out the noise voltage. Okay, we can find out the variance of the noise voltage V of t. Since the noise voltage following Gaussian distribution, and it has the zero mean, and we can find out the variance. Variance is V squared bar, or we can say that it is a mean square voltage of the thermal noise, which is equal to sigma V squared, and equal to 2 into pi kt squared by 3h into r, unit is volt squared. right? So here K, a small k is Boltzmann constant, T absolute temperature, and H is the Planck constant. So this is the variance of the thermal noise. P squared bar is the variance of the thermal noise. And we can find out what is the mean square spectral density of the thermal noise. That is GV of F. So GV of F equal to 2 RH mod F divided by exponential of HF by KT minus 1. Unit is volt squared per hertz. So it's the power spectral density of the thermal noise, or mean square spectral density of the thermal noise. And you can see here the ratio HF by KT. If the HF is very less than KT, then we can modify the mean square spectral density of thermal noise as 2 R KT into 1 minus HF by 2 KT. Means we are minimizing that exponential term into HF by KT, so that we are getting the second expression for the power spectral density of the thermal noise. Uh, and again, we can assume that if the ratio HF by KT is very less than 1, then this second term will be going to minimized. Okay, so that finally we are getting that the mean square voltage spectral density of the thermal noise GV of F equal to 2R KT. Okay, it depend on the resistance, Boltzmann constant, and absolute temperature, right? And similarly, we can find out the mean square current. So mean square current by using Norton theorem is the ratio of GV of F by R squared. By substituting GV of F, we are getting that mean square current of the thermal noise, which is equal to 2 kT by R. So unit is arm squared by per hertz. We can see here the mean square voltage spectral density of the thermal noise. As theoretically, the spectral density of the thermal noise over the long range of frequencies is constant, but practically, the when the frequency is increasing of the thermal noise, the power of the power of the spectrum going to be decreases. Okay, so we can see slightly when the frequency is increasing, the power of the power spectrum of the thermal noise is going to be decreases slightly, and it maintaining the 10 percentage of the maximum value, that is 2k 2 or kt at the frequency of 1000 gigahertz. Okay, even though actually this thermal noise power spectral density is modeled as a white noise. So the white noise means it should maintain the constant power for all the frequency. But practically, when the frequency is increasing, then the power spectrum of the thermal noise is going to be slightly decreasing. That is the observation from this graph. And here we can see that the equivalent circuit of the thermal noise using Thevenin theorem and the Norton theorem. The first circuit shows the mean square voltage is connected in series with the resistance using Thevenin theorem, and second circuit shows the equivalent circuit of the thermal noise using Norton theorem, where the mean square current is connected in parallel with the resistance. And then from the thermal resistor, we can find out what is the available power by using maximum power transfer theorem. As per maximum power transfer theorem, when the load impedance is equal to the source impedance, then the maximum power will be transferred to the load resistor. So the condition is ZL equal to ZS conjugate. Then we can find out the terminal voltage across the load, which is equal to Vs by 2. Then the available power of the thermal resistor is denoted by PA, so which is equal to Vs squared by 4 Rs, where Rs is the source impedance or source resistance. Okay. then we can find out the available spectral density of the at the load resistance, right? In previously we found that spectral density of the thermal noise, okay, at the input side. Now in the load we are measuring what is the available spectral density, which is equal to GA of F equal to the ratio of GB of F by 4R. We already found what is the GB of F, that is the mean square spectral density of the thermal noise, which is equal to 2R KT. So divided by 4R. So finally we are getting the available spectral density at the load equal to KT by 2. Unit is watts per hertz. So the observation is the thermal resistor deliver the maximum power of KT by 2 to the matched load regardless of the resistance. So even though the power is coming from the resistor, but the maximum power does not depend on the resistor R. And you can see here there are two circuits showing. The first circuit showing that the calculation of the available power across the load resistor. Okay, so that is PA. So in that there is a source voltage which is connected with the source impedance ZS. As per maximum power transfer theorem, when the load resistor is equal to the source resistor, then the maximum power will be transferred from the source impedance to the load impedance ZL. So that is PA. That previously we calculated what is PA. PA equal to VA squared by 4 RS. And coming to the second circuit shows the how to estimate the available spectral density from the load resistance or RL. Okay, so in that circuit there is a mean square voltage, mean square spectral density GB of F, which is equal to 2R KT, connected in series with the thermal resistance R. Okay, then we can find out what is the available spectral density at the load resistance R. Due to by using these two parameters GVFF and the resistance, the thermal resistance R. Here there is two example by using that parameter noise voltage and mean square voltage. So first example, we can calculate the RMS noise voltage across the terminal of 1 kilo ohm resistance at a temperature T equal to 29 Kelvin. So the formula for RMS noise voltage across the terminal of the resistance is V squared bar, which is equal to 2 into pi KT squared by 3H into R V squared. It's nothing but the variance of the thermal resistor. Okay. So we know all the K is Boltzmann constant, H is the Planck constant, T is the absolute temperature, which is given 29 Kelvin, and R equal to 1 kilo ohm. By substituting all the parameter, we are getting that RMS noise voltage of the 1 kilo ohm resistor equal to 1.3799 micro volt squared. Okay, so coming to the second example, find the percentage of the mean square voltage that comes from the frequency component in the range mod f less than 1 gigahertz. So this is the formula to find out the mean square voltage of the thermal resistor. Okay, that is GB of f equal to 2R KT into 1 minus HF by 2 KT. So in this example, we consider, because the condition is mod f less than 1 gigahertz, and here we considered the frequency is 10 megahertz. So by substituting that frequency, finally we are getting that mean square voltage of the thermal resistor equal to 7.4919 into 10 power minus 19 volt square per hertz. Next, we are going to discuss about the white noise and filtered noise. So we in the previous session we studied this topic, white noise and filtered noise, and a few more points we are going to discuss by using that another textbook, Bruce Carlson. Okay, the beside the thermal resistors, the many other type of noise sources are Gaussian. Okay, and it has the flat spectral density over a wide frequency range. Okay, uh, so the power spectral density of the white noise is G of F equal to N naught by 2. Okay, that is the main parameter in the white noise, because this is the power, that power spectral density of the white noise N naught by 2. It is, you can see from this, the power spectral density of the white noise, it does not depend on the frequency. It depend only on the N naught. Okay, so where N naught is the density constant. Okay, it is a product of, it is depend on the the Boltzmann constant and the absolute temperature. Okay, and the 1/2 in the power spectral density coming from the fact that the half the power is associated with the positive frequency, and half of the power is associated with the negative frequency. That is the reason here we are using that 1/2 for the power spectral density of the white noise. Okay, so even though theoretically we are assuming that the white noise power is constant for all the frequency, but in reality the noise power is slowly decreasing when increasing the frequency. Okay, and it is maintaining the 10% of the maximum power N naught by 2 at a frequency of 1000 gigahertz. And we can find out what is the autocorrelation function of the white noise. So we can see here the waveform shows the, and the first waveform shows the power spectral density of the white noise. It is a flat, it is a flat and maintaining constant over the entire frequency, from negative minus infinity to positive plus infinity, and the magnitude is N naught by 2. The second waveform shows the corresponding autocorrelation function of the white noise. It is a impulse function, and it has the magnitude of N naught by 2. Okay, so we can get the autocorrelation function of the white noise by taking inverse Fourier transform of the power spectral density of the white noise G of F. And the thing is here, the white noise having DC component, and it is varying from minus infinity to plus infinity. We can consider only one sample from this power spectral density of the white noise. Okay, because each frequency component in the white noise having the N naught by 2. So now consider as a sample in the power spectral density. Then by taking the inverse Fourier transform of the particular sample, we are getting that the weighted delta function. Okay, weighted delta function N naught by 2 as a autocorrelation of the white noise. So the R of t equal to N naught by 2 into del of tau. So which means that it's the weighted delta function. That is the autocorrelation function of white noise. And here we can observe that that autocorrelation function equal to 0 at a tau not equal to 0, which means that the each sample of the Gaussian white noise is uncorrelated, and also it is statistically independent if it is Gaussian. And we can realize the property of the white noise while passing through the loudspeaker. We can realize the white noise properties, and we can sense how it is behaves. Okay, so it makes these sounds like a waterfall. The white noise makes a sound like waterfall, which means it maintaining a constant sound. The white noise maintaining a constant sound, same sound. And then if you consider the source is a thermal resistor, okay, then the corresponding mean square voltage and mean square current of the white noise is 4R kT, and mean square current is 4 kT by R. Okay. Then the noise temperature, okay, for any type of white noise which is coming from thermal or non-thermal devices is expressed by Tn. So Tn equal to N naught by K. But we know that for thermal white noise, that we are representing the power spectral density is N naught by 2. Then now consider the LTA filter. So the input of the LTA filter is a white Gaussian noise, which is denoted by x of t, and it has the spectral density N naught by 2. Okay, then the input white noise is applied to the LTA system. The LTA system having the transfer function h of f. Then the output of the LTI system is also a Gaussian, which is denoted by G Y of F. The input of the Gaussian is white noise, whose power spectral density is G X of F. Then output of the filtered white noise, the power spectral density of filtered white noise is G Y of F, which is equal to N naught by 2 into squared magnitude of the frequency response of the LTI filter H of F. Okay, then we can find out what is the autocorrelation function by taking inverse Fourier transform of the G Y of F, which is equal to y squared. It will give the y squared bar, which means mean square voltage, mean square output voltage, which is equal to n naught by 2 into minus infinity to integration minus infinity plus infinity squared magnitude of frequency response. Okay. So here the observation is the filtered white noise. Since the spectral density of the filtered white noise takes the shape of the squared response, squared magnitude of frequency response of the LTE system. So the filtered white noise produces the colored noise. Okay. Then the colored noise can originate from semiconductor devices, which includes the flicker noise and popcorn noise or burst noise. So flicker noise has the spectrum 1 by f, and burst noise has the spectrum 1 by f squared. Let's consider the h of f being an ideal low pass function, low pass function, which has the unit gain and a bandwidth b. Then the power spectrum of the filtered white noise, power spectrum of the filtered white noise is denoted by G y of f equal to n naught by 2 into pi of f by 2b. Right, is the power spectrum of the filtered white noise. And the corresponding autocorrelation function is Ry of tau. By taking inverse Fourier transform, we are getting n naught b into sinc of 2b tau. And where the pi of f by 2b is the rectangular function. Okay, so which means that the rectangular function having one only for the frequency range from minus b to plus b. Then we can find out what is the output power of the white noise, which is equal to the product of n naught into b. Okay, so the thermal noise in RC network. Now we can see the what happen when the noise is passing through the RC network. What is the output power of the RC network? So that we can consider the input of the RC network as a white noise, and which has the mean square voltage G x of f. G x of f is the input mean square voltage. Okay, input mean square voltage, which is equal to 2 r kt whole square, unit is whole square per hertz. Now the RC network having the frequency response, that is denoted by h of f, is the ratio of the output on the output signal by input signal in frequency domain. Then we can it is depend on the impedance ZC and the ZR. So it is a ZC by ZC plus ZR. You have to substitute the impedance ZC and ZR, and by simplifying, we are getting the frequency response of the RC network, RC low pass filter, which is equal to 1 by 1 plus j 2 pi f RC. And we can rewrite this expression as 1 by 1 plus j f by p, f by b, where b equal to 1 by 2 pi RC is the RC network bandwidth, RC low pass filter bandwidth. Okay, then from this frequency response of the RC low pass filter, we can find out what is the magnitude. So because of it is a complex number, so magnitude of the frequency response of the RC network is 1 by square root of 1 plus f by p whole squared, right? And then from that we can get what is the squared magnitude of the frequency response of the filter, that is h of f equal to 1 plus f by p whole squared into power minus 1, means inverse of 1 plus f by p whole square is the frequency squared magnitude of the RC filter. So here the circuit shows the RC network with resistance with thermal resistance R, okay, and there is a capacitance. Then the equivalent noise circuit of the RC network. So the equivalent noise circuit, there is a mean square voltage source, that is G X of F, okay, which is connected in series with the thermal resistance R. Okay, then the available power of the RC network is Y squared bar equal to KT by C. Y squared bar equal to KT by C. We are getting. Okay, so here the thing is the input is white noise, which has the mean square voltage G X of F. Okay, mean square voltage G X of F, which is equal to 2 or KT. Then the output of the RC network is or RC filter is Y squared bar equal to KT by C. Okay, so for that now we can first you can find out what is the output spectral density, which is G Y of F. Gy of F equal to the product of modulus of HF squared into Gx of F. So where Gx of F is the mean square voltage of the input signal, and H of F squared is the frequency response of the RC filter. Okay, so we already know what is the frequency response of the RC filter and the Gx of F. So we can directly substitute both values. We are getting that output spectral density of the RC network. So in that where B is the RC network bandwidth, which is equal to 1 by 2 pi RC. Now we can use the Fourier to simplify this output spectral density. We can use this Fourier transform pair, that is exponential of minus AT equal to 2a by a squared plus 2 pi f whole squared. Okay. So now we can consider we can take the frequency response of the RC filter, that is h of f squared. Okay, we can rewrite this inverse expression as 1 by 1 plus 2 pi f RC whole squared, right? And this also further we can modify like 1 by 2 RC into 2 RC by 1 plus 2 pi f RC whole squared. Then this second term will be again modified as 2 by RC by 1 by RC squared plus 2 pi f whole squared. Now let A equal to 1 by RC, right? Then we can replace the 1 by RC by A. So we are getting that frequency response of the RC network equal to 1 by 2 RC into 2A by A squared plus 2 pi f whole squared, right? Then by after applying the frequency transform pair equation, we are getting that impulse response of the RC filter h of tau equal to 1 by this value 1 by 2 RC is coming as it is, that 2a by a square plus 2 pi of whole square is rewritten as e power minus modulus of tau by RC. So therefore, finally, we are getting the autocorrelation function of the output of the RC network. Output of the RC network, that is R y of tau equal to 2R kt into 1 by 2 RC into e power minus tau by RC. So the first term is coming from the mean square input mean square voltage. This term is coming from the impulse response of the RC filter. Then the 2R will be cancelled. Then finally the output power of the RC network equal to autocorrelation function of the RC network is kt by c into exponential of minus modulus of tau by RC. At tau equal to 0, we are getting the output power of the RC network. Therefore, Ry of 0 equal to kt by c. Because at tau equal to 0, the autocorrelation function will give the mean square value of the of that particular signal. So that we are getting the output power of the RC network equal to kt by c. So now we will consider one example. Consider the resistor at a room temperature T, and the capacitor C equal to 0.1 microfarad. Then what is the output power of the RC network? Okay. So the formula is y squared bar equal to Ry of 0, which is equal to kt by c. K is Boltzmann constant, T is the absolute temperature, 270 divided by 10 power minus 7. It will be equal to 4 into 10 power minus 14 volt squared. So that is the available output power of the RC network when the input is the white noise. So this. So y squared bar equal to kt by c is the available output power of the RC network. Okay, when the input is the thermal noise. Then from the noisy component, we can find out what is the equivalent bandwidth of the noise. Okay, because if you consider the white noise, it has the bandwidth from minus infinity to plus infinity, but after passing through the filter, the bandwidth of the white noise will be limited. With that bandwidth is depend upon the bandwidth of the particular filter, right? Okay, so the filtered noise usually has the finite power. The average noise power of the filtered noise is n, capital N equal to n naught by 2 into integration minus infinity to plus infinity modulus of h of f square df. So this is the frequency response of the filter. Okay. So and then the noise equivalent bandwidth is Bn. So the Bn equal to 1 by G integration 0 to infinity modulus of h of f square df. So which means that the noise bandwidth depend on the frequency response of the filter. Okay, frequency response of the filter. So that by integrating the frequency response of the filter, we are getting the what is the equivalent noise bandwidth Bn. So in that G is the modulus of h of f squared, maximum value of the modulus of h of f squared. Okay, that is the G. So from that we are getting G Bn equal to 0 to infinity mod h of f squared df. So that we can get the average noise power. So average noise power or filtered noise power n equal to n naught into G into Bn. Because here this term is replaced by G into Bn, so that we are getting that average noise power n equal to n naught into G into Bn. Now consider the filter center frequency f equal to 0. So at that condition f equal to 0, the G becomes 1 because G equal to h of 0 squared. Okay, so at f equal to 0, G equal to h of 0 squared. So at 0, the G becomes 1. That is the response, frequency response of the filter at a frequency f equal to 0. That is the unit gain. So hence the filtered noise output power n equal to n naught into Bn, or it will be equal to Kt by C. Okay, then we are going to next we are going to discuss about the band pass noise. Okay, the band pass noise is actually which is coming from the all type of analog communication system. Okay, so this noise is affected in all type of analog communication system, and this band pass noise is arising when the white noise is passing through the band pass filter in the communication receiver. Okay, now you can see from this diagram, this block diagram shows the complete setup of the analog communication system, continuous wave communication system. It has the two section, that is a transmitter section and a receiver section. In the transmitter section, the input signal is denoted by x of t. It is given into the transmitter, and its output, the transmit power is denoted by st. The st equal to square root of L into xc of t. Okay, the here the xc of t is the modulated signal, and L is the transmission path loss. L is the channel transmission path loss. Okay, the second plot shows the channel, and the L indicate the transmission loss of the signal is denoted by L. Then the output of the channel is the modulated signal xc of t. Okay, the output of the channel is a modulated signal xc of t. Okay, coming from the channel. The channel may be a wireless medium or wired medium, and the corresponding the received power from the output of the channel is SR equal to xc squared bar. Okay. Then after that, the noise will be added. The noise has the spectral density G of f equal to n by 2. Then there is a receiver section. Receiver section consists of the three blocks. That is a band pass filter and a detector, then low pass filter. In the band pass filter, response is denoted by H R of f. Low pass filter response denoted by HD. Okay. And after the input of the band pass filter is white noise. It has the sparse filter density n naught by 2 over the range of frequency from minus infinity plus infinity. But after passing through the band pass filter, that noise becomes the band pass noise. It has the bandwidth of the band pass filter. Okay. So the output of the bandpass filter, that receiver is consist of V of t equal to xc of t plus n of t. Is a received signal from the receiver. So now consider the x of t is the low pass signal, and its magnitude is less than 1, and the power of the input signal is x of xx equal to less than or equal to 1. Okay, here the channel transmission loss is denoted by L. The modulated signal at the output of the channel, that is xc of t. The carrier amplitude is AC. The received signal power is SR. It is the ratio of ST by L. Okay, which is equal to xc squared bar. Then here we can model the bandpass filter. So the bandpass filter, the receiver is modeled by considering the pre-detection portion of the receiver. The pre-detection portion of the receiver is modeled as a bandpass filter whose transfer function is HR of f, and it has the unit gain, and bandwidth is BT. Then so with the assumption of the additive noise at the receiver, Then the total signal plus noise, okay, at the that means the received signal at the detector is uh, expressed by V of t. So V of t is the received signal at the detector. V of t equal to Xc of t plus N of t. Your Xc of t is the modulated signal. N of t is that pre-detection noise. N of t is the pre-detection noise. Okay. And this the received signal V of t also represented in another two forms, like we can represent in terms of envelope and phase, or we can represent in quadrature form. So you can see the first equation, the a V of t is the envelope, and pi V of t is that phase of the received signal V of t. Or in terms of quadrature form, there is a in phase component first time, the second time is the quadrature component of the received signal V of t at the receiver. Then since the receiver is consists of the one band pass filter, one detector, and then one low pass filter. So after signal detected by the detector, it again passing through the low pass filter. So the demodulated waveform pass through the low pass filter with it has the frequency response HDFF. So finally, we are getting the output YDFT at the destination. Okay. And with the assumption of the signal and noise are statistically independent, we can find out the mean square voltage. Okay, V square bar, which is equal to at the detector, which is equal to Xc squared bar plus N squared bar. Or we can write like in another notation, which is equal to SR plus NR, which means SR is the received signal, received data power. Okay, received signal data power, and NR is the received noise power, received signal power, received noise power. Okay. So band pass noise, as we know that the band pass noise is coming when the white noise is passing through the band pass filter. So the filtered output noise has the spectral density. So before passing, you can see from this system, okay, it's a bandpass filter. The response of the bandpass filter, HR of F. The input of the bandpass filter is G of F. It's a white noise. The white whose spectral density is N0 by 2, and the output of the bandpass filter is G N of F. It is the product of N0 by 2 into the squared magnitude of the frequency response of the bandpass filter. So which means the spectrum of the white noise is limited to the bandwidth of the bandpass filter. Okay. So here it shows the power spectrum of the filtered white noise. Uh, After passing through the bandpass filter. So it shows the GN of F, the output to filtered white noise. The magnitude, maximum magnitude is N naught by 2 into the squared magnitude of HR of F. Okay, it has the bandwidth BT, which means the bandwidth is limited. The white noise bandwidth is limited after passing through the bandpass filter. Okay, then the pre-detection noise power we need to calculate. So at the detector, we can find out the mean square voltage of the received signal, that is V squared. B squared bar equal to Xc squared bar plus N squared bar, where N squared bar is the pre-detection noise. So pre-detection noise power. So we need to calculate that one. So that is the pre-detection noise power, that NR equal to N squared bar. It will be calculated by considering the filtered output noise. that is a Gn of f. That is the filtered output noise spectral density. Okay, so integration of minus infinity to plus infinity Gn of f df. So which is equal to n naught into bt. By integrating the spectral density of the filtered white noise, we are getting the pre-detection noise power equal to n naught into bt. Then so after getting the noise power and the signal power, we can find out the what the signal to noise ratio or the pre-detection signal to noise ratio. Okay, which is equal to n s by n signal to noise ratio at the receiver. The subscript R indicate the at the receiver, which is equal to the ratio of the received signal power divided by the received noise power. NR is the received noise power. Okay, that the received noise power is the product of N naught into BT, where BT is the bandwidth of the band pass filter. Okay, thank you. So in that session, we studied the few more points in the thermal noise, and we analyzed the thermal noise in the RC network. Then we studied about the what I mean by bandpass noise. In next session we'll discuss about the some properties of the bandpass noise. Thank you.